And so our last speaker before lunch will be David Elbaz from Paris, talking to us about star formation in the distant universe.
Hi. So the question I would like to ask is, are we seeing an excess efficiency of star formation in the distant universe? And I will try to say, what does it mean? Because it's not a clear question. And this is going to be the papers I will be talking about during this presentation. Well, there is an excess UV luminosity function at high Z, and I refer to the beautiful talk by UC-HiPACC that we heard this morning, who summarized that very well. And the question I would like to address here is that excess of galaxies that we see in the UV luminosity function associated with an intrinsic stronger star formation efficiency in distant galaxies? And as Yuchi mentioned, there are various explanations that are possible to explain that, not just simply the star formation efficiency. One of them being stochasticity of the star formation. You can have galaxies popping up from a normal luminosity function, and just because of stochasticity, you think there is an excess, but in fact, it's just very short time ever. So with the law of Tesla, we addressed that by doing SED fitting and trying to see if there had been an excess star formation stochasticity in the distant universe. And we do find an increasing stochasticity of star formation at redshifts greater than 9 as compared to the secular star formation when you look at, for example, timescales of the order of 100 million years. Now, is that enough? And in practice, when you compare that to what would be expected to explain the excess UV luminosity function, like in the Shen et al. 2023 paper, we find that this stochasticity is 3 times typically lower than what you would need. So stochasticity is there, but doesn't seem to be strong enough to explain it. This is based on SED fitting. You would need to do that better with spectra when it would be possible. AGN activity, well, in Steve Finkelstein's paper, he mentioned the fact that there is no clear UV signature of AGN, so for the moment, it's not necessarily favored, but okay, again, they could be hidden. There has been suggestion that you could have a lower dust content, but that also is not very clear to me because it's lower with respect to galaxies that were a bit biased towards high dust content in a more nearby universe, so not clear. Top heavy AMF, that's the question we always have. I mean, we will always have during our lifetime, I think, so I don't want to address it here. But then there is this question of the efficiency of star formation that requires a stellar mass. And that's a bit tricky because the stellar mass at redshift 7 or 9, for example, is not something you can easily get. So we've all seen this Labbe et al. Paper claiming that you have a number of galaxies that have been called the 6 impossible galaxies in the literature. So if they are impossible, that's probably because they are really impossible, but and they are supposed to be galaxies including one at 10 to the 11 solar masses at redshift 7.5, and if you compare that to the stellar mass functions that have been expected and measured or derived, it's a factor 1,000 at redshift 9 more. You would need a volume 1,000 times larger than the ones that have been probed to get such a galaxy. So this suggests that something is going on, if it's true, if the stellar masses are correct, if etc. And if that was correct, you had this Boylan-Colchin paper in 2023 claiming that the efficiency of star formation, even with an efficiency of conversion of baryons into stars of 100%, you would not even get that galaxy, and you would start entering into questioning cosmology. And there has been papers starting to say that you have to question cosmology with an early dark energy to make more space in time to make those galaxies, or to modify the power spectrum. There have been several papers, and you can even find on the web questions about the Big Bang, did it even happen? Or you could have galaxies formed before the Big Bang. So this is very efficient. But before changing the generic, our series of the Big Bang theory, and before changing the song of the Big Bang theory, we have to think a bit more and make sure that we didn't make mistakes somewhere, because I do like this series, as it is. So one thing that people didn't mention a lot is the possibility that there could be wrong stellar mass estimates when you don't get the rest frame around 1 micron part of the SED. And usually people were claiming that with James Webb we're going to get robust stellar masses in the distant universe, but at redshift 7 or so, it's not going to be that clear. Already at redshift 5.3 here, you can see in this study by Tao Wang et al. That you will overestimate the stellar mass by about 20% for this galaxy without MIRI, but at redshift 7, you will underestimate it by typically a factor of 3 or even 6 or even 10, depending on the cases. So most probably those galaxies at very high redshift have stellar masses that are overestimated. And if you decrease the stellar mass by a factor of 3, then you go back to a normal efficiency of star formation. So that's, for example, here, compared to the model that was presented by Lee and Lee et Dekel et al., which is in dotted lines here, observations agree with an efficiency of 20%. Maybe this model is not the correct one, but at least it saves our series, the Big Bang theory, so I like it. Now, going back to the more reasonable redshift range of around 5 or 5.5, where you can get robust stellar masses even without MIRI. So what we did with Mengren, Xiao et al., using the data from the FRESCO survey by Pascal Husch et al., is to study galaxies that are red and selected to have a Z-spec between 5 and 9. So here you have real Z-specs, and we have 36 of such galaxies, and for which we can derive stellar masses, including 3 which are really edge dropout, so these so-called optically dark galaxies that you can only see above 4 micron, and you don't see in the HST bands, for example. And when you look at those galaxies, indeed, you find that the vast majority of them have an efficiency that is even lower than 20%. So the line here that you see, is, as usual, is that you take the dark matter halo mass function in the volume that you're probing. You take the most massive dark matter halo, and if you had a 20% efficiency of conversion of baryons into stars, you would be on the dashed line. And all those galaxies are consistent with lower values, and so depending on their dark matter halo mass and baryon fraction, they're going to be consistent with 20% conversion fractions. And you have still some outliers, these S1 and S2 and S3 galaxies. Those are the edge dropout galaxies that have typically a 50% efficiency of efficiency of conversion of baryons into stars, even for the most massive dark matter halo. So there is some kind of high efficiency of some of those galaxies. We do also see some at redshift 7 which have an excess, but again, here the stellar masses could be overestimated, so we don't insist on those. And indeed, if you play this game of trying to see how many volumes, like the FRESCO volume, you would need to get at least one S1 galaxy, the most efficient one, you would need 1,000 of them. So you're back to this problem, but it's low statistics, of course, low number of statistics, but there is something going on. There is possibly some efficiency of star formation, not questioning cosmology, but at least questioning the efficiency of star formation in those galaxies. Now, when you look at those galaxies, even though they have high star formation rates, they are on the main sequence at their redshift, just that they are very massive. So that's why they have high star formation. So that's weird, because they are very efficient galaxies. They have a very efficient conversion of baryons into stars, and yet they are on the main sequence. So usually people were claiming that the main sequence was the place where you have like secular non-star bursting galaxies, and yet you have very efficient star formation in galaxies in the main sequence. So what I like to say is that dust hides diversity, and we have something similar to the relation that was found by Max Kleber in 1932. That is, that if you look at the radiation of an animal, which is its metabolism, that you measure the metabolism of an animal by its temperature and its radiation, it's proportional to the mass, and squirrels and elephants, they are on the same relation. But a squirrel is not an elephant, I can tell you, because if one walks on your foot, it's going to be very different. So you do have diversity hidden in such relations. So the fact that a galaxy is on the main sequence doesn't mean it's not a starburst. And indeed, what we found by measuring the dust mass and the dust content of galaxies at redshift of the order of 2 to 4 with ALMA, we could derive the depletion time, so therefore the time it takes to consume the gas inside the galaxy, and you have a subsample of galaxies shown in red here with a depletion time of the order of 100 million years. So they are really starbursts because you cannot, they're going to consume their gas in 100 million years, so it's not a typical star formation event of galaxies on the main sequence, and yet their star formation rate for their stellar mass is on the main sequence. So we call them starbursts hidden in the main sequence, and that shows that there is a diversity that is hidden by dust in the main sequence. The question is, are those galaxies just galaxies experiencing a burst inside the main sequence, scenario 1, or are those galaxies former starbursts that went up above the main sequence and then are going through the main sequence, and then you're just observing them there, but in fact they are just passing by. So to test that, we modeled the past star formation history of those galaxies with, again, acidificating with Lorsiesla, and those are the arrows. And what we see is that those dusty starbursts shown here with the arrows with a black line on them are not coming from above. And in fact, the starbursts here are galaxies moving up there, and those starbursts here are just galaxies moving within the main sequence. So we don't see evidence that it's scenario 2, but more the scenario 1. So that's something happening within the main sequence. Now, trying to understand what's happening in those galaxies, we did some SED fitting resolved inside the galaxies thanks to the high resolution you can get with the James Webb. And what we found, I don't have much time to go into the details, is that the stellar mass distribution of some of the star-forming galaxies which have an excess star formation, the dusty star-forming galaxies which are very dusty and optically faint, which are shown in red, have the same stellar mass distribution than passive galaxies, and they have an excess attenuation in the center, so concentration of dust in the center as compared to the typical star-forming population. And that excess is partly due to the fact that stellar mass, when you have an increase of the stellar mass, you have an increase of the dust content. But the red line here is showing you that even at the same stellar mass, the population of dusty star-forming galaxies are showing an excess of attenuation, which is due to a compaction event. Now, it turns out that when you look at the typical stellar mass where the fraction of galaxies that are dusty starburst and have a more compact star formation is taking place, it's typically above 10 to the 10.4 solar masses. So the red and yellow line are the parallel evolution of the passive and compact dusty star-forming galaxies as compared to the blue, the normal star-forming galaxies. And above 10 to the 10.4, they become dominant, those compact galaxies that are already having the distribution of stars of the passive galaxies. So they are progenitors of compact passive galaxies. And that suggests that the bulges are formed in situ and not by mergers afterwards, but you are witnessing the in situ bulge formation in those galaxies. So this is the kind of scenario we are talking about, the kind of compaction within the main sequence, typical of what Avishai is mentioning in his paper, and then the galaxy is going to have a slow downfall of star formation afterwards. Now, what's interesting is that these galaxies happen to be falling. The fact that you have a high mass range where you have this building of the bulge of galaxies and where you have a progressive downfall of star formation can be seen with the bending of the main sequence. And the transition mass between the normal slope of the main sequence and the part which is bent, when it is compared to the expected transition between the cold and the hot accretion, turns out to be falling at the mass where you would expect that transition to take place. So to do that, you have to convert the stellar mass into a dark matter halo mass using the Bernoulli relation. And if you do so, you find that it seems to be a signature of a change of regime in the accretion. And what Emmanuel Edadi did was to extend that study even to galaxy clusters, where you could even see some starts of signature of this transition between cold and hot accretion regimes. So accretion seems to be playing a key role in this change of regimes in galaxies. So if I summarize my presentation here, what I mentioned in the beginning is that stochasticity is there, but is not strong enough to explain the excess UV population in the distant galaxies. The stellar mass of galaxies at redshift 7 suffers from an overestimation that is nearly systematic if you don't have NIRI observation. So you can be sure that a large part of the excess efficiency of star formation is just due to the fact that the stellar masses are wrong. Not applying to the UV, but to the stellar mass. Now, excess versus what? Cosmology, probably not. But there are some cases of galaxies with a very high efficiency of star formation. Those are on the main sequence, but the main sequence does have some hidden diversity, hidden by dust in it. And that is increasing, this diversity is increasing up masses above 10 to the 10, 2.4 solar masses, where you see more compact star formation, more dusty. And we believe that this is bulge produced in situ in galaxies that are going to become passive in the near future. So there is a key role of cold accretion, which is probably playing a key role in explaining the bending of the main sequence. And we need a mechanism to explain this excess efficiency of star formation. So there is the feedback-free starburst model, but I like also the idea that that black hole formation may also induce a positive feedback effect in the distant universe when galaxies were very compact. But this is, of course, something to be investigated. Thank you.
All right. All right, so chair's prerogative, I'm going to ask the first question. So you were talking about the main sequence a lot. At redshift of 5 and above, though, how meaningful is this idea of a main sequence?
So the whole point of the main sequence is the dispersion, because the fact that bigger is bigger is not really physical relation. So it's true that the dispersion of the main sequence is the key point, and that's why, in fact, we do see higher dispersion and higher stochasticity at high redshift, and even at redshift 5, 7, etc. So we don't keep the exact same tight dispersion. Yet, then the question is, when you have a dispersion of 0.3 dex, 0.4 dex, do you still call it a main sequence? So you're right that the definition has to be put between quotes, because indeed at redshift 5.5, we find something which is not far from 0.3, so we would call it a main sequence, but when you go at redshift 7, it's polymetric. So you're right that this is bigger is not.
Right. Okay, other questions. Let's go to Harley. Oh, and then we'll go back.
Thanks for the. Is this on? Yeah, thanks for the very nice talk. I have a couple questions about the stellar mass and the 3x overestimation. So, I've looked at tons of galaxies between redshifts 4 and 8, right? And if you just compare their stellar masses versus the F444 flux, the wide band, you find that there's a 3-dex range for the same F44W flux, which is a little bit surprising because in theory that should be probing the stellar masses. And what it seems to be related to is the assumed star formation history, which isn't surprising. And this is especially problematic if you have a super strong starburst where the most recent burst is outshining it. And in fact, to sort of add to that, in the few studies that have done the spatially resolved star formation histories, I'm thinking about Pascal Osh's group, they found that in fact it was underestimated by about a dex up to. So I was wondering if you can comment on sort of the difference between this 3x overestimation and then those other galaxies where it seems to be wildly underestimated.
So you would say that you would underestimate. What do you compare? You compare with and without the 4.4 micron? But alone. Yeah, but here so we haven't tested that point of taking the 4.4 micron alone. Yeah. 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 That's a good point. I mean, so you do talk about having just the 4.4 micron alone compared to the 2. Yeah, okay. Because that I don't know. Yeah. So the spatial result, it's all, well, what we found at closer redshifts is that the place where you have the star formation and the place where you have the bulk of the stars and the place where you have the bulk of the UV are not necessarily the same. So the parts you're assuming a fit of a single population and a single region. In fact, the light is coming from different regions. So it's why when you correct the UV for attenuation, for example, you don't get the accurate star formation because it's not coming from the same part. Now for the stellar mass, what until now what we were finding is that the part where you have the large wavelength band is centered at the same place than the stellar mass. So what you just said, I need to investigate what you just said because for me it's new, and I would need to understand what you're saying a bit more. Because if you're right, I mean, we haven't tested just that thing, but if you're right, maybe we are missing some key points, and we should discuss because I need to understand better. I don't have a clear answer to that.
Yeah, sounds like a good lunch conversation.
Yes.
All right, right next to him. There you go.
I have a very quick question. So for the star bursts along the main sequence that you are talking about, the star formation rates that you are quoting are from IR, right?
Yes.
How about their optically inferred star formation rate?
So their optical well, those galaxies, if you correct, let's say if you use the UV corrected for attenuation, you will see that they are not anymore starbursts because the star formation rate of those galaxies is underestimated if you don't take into account the infrared.
So, but how about after the dust correction?
After a dust correction, you still underestimate most of those galaxies the star formation.
Okay, one more question before lunch, if anyone has a burning one. Nope. Okay, let's thank all of our speakers again.